Okay, guys, thank you very much for being here. I'm kind of surprised by the turnout, and well, I hope you guys enjoy it. I'll pretty sure to try to put up a good show. But before we start, I just want to put a warning here. Okay, you might have stumbled in the wrong room. Okay, this is about defend. I'm not doing any vanity hack. Okay, no cars were damaged. Nothing happened. Okay, so. If that's what you're looking for, probably there's something on the other rooms, okay? But we're actually trying to build something here, all right? So, a word to the wise. Also, there's going to be math, okay? So if that offends you in some way, okay, now's also the time to leave. I will not be held responsible for stuff that gets shown there, specifically around math. So, anyway, any takers? Are we good? All right, so let's begin. Okay, first of all, just before we actually get started, I want to give you guys some idea where I'm coming from, okay? So I've actually been doing information security mostly as a defender for like 12 years. And the reason why you might have never heard of me, and I'm totally cool with that, is because I've been doing this in Brazil, all right? So I've actually been running an information consultancy company out of there for this time period. And I got exposed to a lot of things, and as I traveled around the world, it became very clear to me that the problems are pretty much the same. We're all fighting the same fight. Doesn't really matter where we're from. And the fact is, for the past 6 or 7 years, my main attribution was SOCs. Okay, so I was running the monitoring teams, I was setting up SIMs, I was setting up log management solutions, and for as long as I can remember, and for all the different technologies that were the leaders, and they're not the leaders anymore, and now some big guys are there. So, for all the movement, if there's something that they can hurt you with, I have been hurt. I have all these battle scars of things that don't work, and things that are very, very hard to get right, and This is where I'm coming from. This is really, really where I'm coming from in putting these ideas forward. So I haven't been into machine learning for a long time. It's been like almost a year or so where I'm started dabbling with this. I've been doing a lot of self-study research, and I've been participating on Kaggle competitions. I don't know if you're familiar with it. Anyway, this is my first presentation. I hope you guys enjoy it. So what we're going to talk about, okay, first of all, my pet peeve with security monitoring and why it doesn't scale, it doesn't work, how machine learning could potentially save the day, some considerations about data gathering for InfoSec, which the kind of thing that makes us different than any other field that works with machine learning, and the most of this talk is going to be about a specific model that I built to help predict malicious activity from log data, okay? I'm going to go through a lot of detail about how this was put together. If you guys look up the white paper, there should be even more detail there. And more than happy to have any one of you tell me that I'm completely wrong, because that will totally free up my time. I'll be able to do something else. And not really, okay, this is working, I should keep on this. And anyway, I'm talking about the project I'm putting together for this. Some ideas on how to break this thing that I built, and what I think some of the deficiencies are. And of course, some future direction. Anyway, let's get to it. Okay, we all have a lot of logs, right? And all these logs are sitting now at your SIM solutions, at your log management solutions, and we're doing that mainly for compliance reasons, right? We want to make sure that the fluorestation wood is good. And it's a fact of life, in the sense that if you will look like, I don't know, maybe 7, 8 years ago, only the really big guys would be actually logging and storing this stuff. But we got a lot of regulations like HIPAA and like PCI. So every mom and pop shop today, they will have some sort of log management solution. And they will be extracting next to zero value out of that. They will not have the people to do this. They will not have the capability. And the fact is, the tools don't really help, okay? So I'm not here to bash on the tools, but I just want to show some things that some information that I've been gathering. So if you look at Gartner every year will tell how everyone is so unhappy with their SIM vendors, and they're switching SIM vendors like, I don't know, every year or so. They will just forget about it, and then, okay, I'll try. A different one might change it. So they say numbers as high as 90-something% of people will get a lot of breaches. They won't be able to detect it even though they have this deployed. And this is really a favorite one of mine. It was from last year from SANS. And so the thing that people complain the most, okay, and I do apologize that there's no horizontal scale on this bar. I couldn't have no idea, but it seems bigger than the other ones, is what they can't do with SIM solutions, hold on, identification of key events from normal background activity. Think about that for a while. It's like you buy a car, and your biggest problem with the car is that you can't get it from point A to point B, right? You brought the car to drive. You bought the car to go places. So the main thing that people are unable to do with SIM solutions is what they were designed to do. There's something wrong, okay? And I don't think, although I do have issues with the way you configure SIM solutions, okay? So this is a generalization, but if anyone here has had experience with working with SIM deployments, they will kind of relate to this. You'll either be able to create some sort of threshold in an event or a group of events, so something happens X times, or you're composing that something happened with another something based on the same IP address, based on a timing recognition of sorts. And most of the SIM configuration, which many people that I met, I know it's actually an art, right? You have to really be skilled. It's pretty much iterating on this until the customer is satisfied. Or the money runs out, which also happens from time to time. And the feeling I get is that, I mean, it's kind of was built, it's a kind of tool that was built for people to make money out of consultancy. I wouldn't say it's the biggest offender of that. That would probably be identity management solutions. But, yeah, sorry. But anyway, it's tough. It's tough. So behavior analysis got into this, which is very cool for helping with the access. But even so, if you don't really know what you're doing, and it starts telling you, oh, this is normal. Okay, so everything that's outside of this deviation of normal, you should be alerted on. I mean, I've had a number of cases where the normal was like on the last day of the month, so everybody was hot on the ERP, you know, the ERP solution, and then that was not the normal the next day. So anyway, people were unhappy. So, I mean, it's tough, okay, but it's not a tool problem, not exclusively a tool problem. So I know a bunch of guys, okay, that's my log management slide. They're doing a great job managing that log. They do a good job, but I mean, I know a handful of people, okay, that if you give them time, I mean, like, I don't know, 6 months, a year, right? They will make the current tools that we have really sing, okay? And, but I mean, they're very few and far between. And more people are getting logs, pretty much everyone, and they don't have these people to help them. They will not have these people to help. They will not have the money to pay. They will not be able to hire these people. And I don't know, I feel that there's a disconnect, okay? So there's a leading SIM vendor, which I'm not going to name, but some of you might know. They actually have, it's a month-long training session. It's 20 days, 4 weeks of training. Not a single hour of this training is dedicated to, okay, these are the content that we have out of the box, and this is how you use it, right? So, all right, okay, you learn a lot about how build new dashboards, how build new rules, and that's all very good and important, okay? But why are we buying this? And everyone is up there, oh, I have this much correlation rules, and I have this much dashboards. If we, as a community, are not being taught how to use them, right? For our customers, for our organization. So what's the point? What is the point? These things are very hard to configure properly. And that's the kind of peeve that I have. That's the suffering I've faced for the past 7 years. And next up, right? We're going to have big data. There's going to be a whole lot more logs. And guys, I do believe that's the right direction, right? We have been playing with SIM. We have been playing with log management. And those are nothing more than vertical data warehousing solutions, okay? But for some reason, on the information security, we have been living in the 90s in a world where columnar databases had not been invented yet. So we're trying to do really hard data warehousing and data mining on relational databases. Come on, guys. I mean, it's not going to scale. It's not going to work. So this is happening. Of course this is happening. And it's a great move. But the way I feel about this is that a lot of people are going to buy this, and they're going to get very frustrated because still they're just aggregating more logs. They're not really getting the intelligence out of it. And oh, I have a cool analytics dashboard. Who is going to run the analytics dashboard? You know? So yeah, I mean, these guys, I know some very, very talented IR guys, incident response, sorry, and but they're not statisticians. They're not data analysts. They might even learn, you know. But how many do you really feel like are going to be good at that, and they're going to be able to do a good job? And I think it's going to dwindle down this already very small pool of professionals that actually can make this the SIM solutions work. It's going to be even dwindled down, and we need help. And that's the main point of my talk. We're not going to get there without help from robots. Okay, so the robots, in a way, they are one of the they really can help. I mean, if there's a machine generating all this data, okay, why don't we get another machine to talk to it, right? They sort themselves out, and they just tell us what I need to do, right? I don't have time to eyeball all this stuff. So this is what I'm coming from. I've worked with SIM my whole life. Okay, not my whole life, 6 years. Oh God, that would be terrible. And I really enjoy it, and it can really solve some very, very interesting problems. But I think we're losing touch with the fact that there's actually a lot of people that need this deployed that don't have this capability to tune this incredibly complicated machine to actually extract something of value. Okay? So, enter machine learning. Right? And I mean, I'm very conscious that I'm definitely not the first person talking about this, but the approach I'm trying to take is really not to boil the ocean. So I created a tiny little thing that has been getting some interesting results, and that you could potentially replicate or do something very similar with very, very little effort, just based on the log data that you have. But I just going to go to a quick primer on machine learning just to make sure we're all pretty comfortable with it. It's not dark magic. It kind of looks like sometimes, but I just want to make sure that we're pretty much on the same page. The biggest point there is that you don't code the problem. You don't code the program. You code a way for the program to interpret the data and then give you results out of it. So it's pretty much like telling a toddler that is a chair. Okay, the first chair you show the toddler, it will think that all the chairs are exactly like that. And if you just don't have any other chairs around, that will be it, right? But then if you start telling, okay, this is a chair, this is a chair, this is a chair, then our brain is able to create a general model of what a chair is, right? And we'll be able to recognize chairs anywhere. Okay, so that's a very gross simplification, but that's the way we have to think about how these processes work. If we had enough data, okay, and of course we don't, that's the whole point of the incomplete information part on the title, we could potentially generalize, okay, an attack is an attack, and just have to deal with it. But we're not quite there yet. So just to make sure you guys know that this is controlling your lives, some very brief applications. So sales, of course. So everybody uses Amazon, I hope. I don't know. I like them, but I'm not endorsing anyone. You have like recommendations for you. So they do a technique called collaborative filtering, where they look for people who bought things similar to you. Okay, you put them all together in a kind of a category, and they will. Okay, if all these people that bought things that are similar to you, some of them bought these additional items that you didn't buy, so I'm going to show it to you because you probably want this too. So the way they do this, they have like this billion row, billion column matrix, and they do some weird calculations around this, but this works pretty well. You occasionally get like, I don't know, My Little Pony book or something like that. But that's just a part of the ride. Machine learning is not perfect, and I don't think it's supposed to be. Trading, which is another example of the way machine learning is a big part of our lives. Most of all the high-frequency trading, I mean, high-frequency gets its name from that. It's computer competing against each other. So there are different machine learning algorithms. It learns to read what's happening in the market, and then it makes its bets. It sells, it buys, and shorts, and all the crazy things you can do. And that's actually a nice picture. It was when it actually crashed, right? So the computer algorithms, I don't know, they got crazy. One got mad at each other. Everyone started selling at the same time. It almost crashed. I don't know. I think it was New York stock. I'm not entirely sure, but they figured it out quickly, and it got back up, and everything went back to normal. And finally, image and voice recognition. And Google is like leaps and bounds ahead of everyone in this. This is actually a picture from a research program they had recently, where they put like, I don't know, 60,000 computers in a machine learning cluster to figure out pictures of cats. So I want to identify pictures of cats on the internet. It knows they really know the target audience. So that's cool. So, but anyway, they could generalize it enough, and they were using a new technique that's called deep learning, where they're pretty confident what a cat is. Yeah, that's awesome. That is awesome. So what about security? Haven't we been doing stuff like that? Actually, we have. So most of the fraud detection system, they will use some sort of machine learning with some weird heuristics. And everybody keeps their cards really close to their chest. But the basic gist is that they will have a variation of clustering, which I'll touch in a little bit more detail later. But they will figure out which category you're on in a way. They don't really know you, they don't really care, but you're similar to this group. So if you do something that's too different from what this group usually does, okay, there's something wrong here. It's not you, it's someone that's using your account. And usually the ability that these systems have to actually do a good job, it usually depends on the number of dimensions they have and how much data they can get from you and things like that. But anyway, everybody keeps their card really close. So network anomaly detection and a lot of the analytics we get in the market right now are usually just a statistical analysis, just really, like I said before about behavioral analysis on SIMs. Okay, this is the norm. If something happens, I'm going to flag something for you up here and up there. That has its values. It helps, definitely helps with a lot of things. I mean, it helps you get an understanding of if something really weird is happening, but it's not really machine learning. I'm pretty sure there's some vendors here who will disagree with me or throw some tomatoes, but I would love to be proved wrong. I would love to know that there's more people actually going into deep down and this kind of things. And finally, spam filters, you know? You guys remember the Bayesian filters? Yeah, that's it. That's machine learning for you. And we've been doing this for a while now. And I was digging some, so I had another talk which was more like Introduction to Machine Learning for Security People, which was in B-Sides. And I actually digged up a paper from Microsoft Research from '98, where they was discussing the applications. They had all sorts of results about using Bayesian filtering for spam. And I don't know about you guys. I didn't read the whole program. How many talks do we have today about spam filtering? You know, yeah. So I would dare say that this is almost a problem that has been solved. Of course there's phishing. Of course there's spear phishing. But that's not spam. That's someone that's crafting an email specifically for you. Right? It has all the proper language. It has all the proper links. Yeah? Yep. Hello? Is it better? Yeah, okay. So they will be... Of course, there will be specific attacks against it, which pretty much means send an honest to good email. But I don't know, I've been with Gmail, and I really don't want to be like celebrating Google or anything like that, but I've had them for like since 2004. I've had the Gmail. I'm pretty sure every single spammer in the world has this account already, okay? I can't remember the last time I got honest to good spam. Of course, there's all the crap I sign up to, right? But that's like the CAN-SPAM Act, they are allowed to go through. And there's an occasional phishing, good constructed phishing, but honest to good spam, when was the last time in one of these guys that have access to a really, really, really huge data set, haven't got spam? This is machine learning, guys. This is what machine learning does. So, different kinds, just to make sure we're on the same page. You got your supervised learning problems, which is pretty much you give the data to the computer and you give the label to the computer. So I present a chair to the computer and I say, computer, this is a chair, okay? So then it can, yeah, that's exactly how it works. And then you can, okay, good, okay, now this is a table, cool, table. So if I give it enough chairs and tables, it should be able to tell them apart, okay? And that's a classification problem, all right? And I named some algorithms there, so you might have heard of neural networks. Neural networks are usually used as a classification problem. Support vector machines, which I'll talk a little bit more, because that's actually one of the algorithms I'm using. Naive Bayes as well, which is the thing that fused spam, what we were talking about. But all of these can be, with some math voodoo, they can be generalized as well to regression problems. So a regression problem is like, okay, here are chairs and here are tables, all right? But let's say I get a stool, right? It's a weird stool, right? You could sit on it, and it's a little bit higher, so maybe you could put stuff on it. It might really get the computer confused, because it's kind of halfway there, halfway between a chair and halfway between a table. So, I mean, the regression problem, if I had my chair at 0, or -1, and my table at 1, at 0, okay, don't tell me if it's a chair of a table, tell me how much of a chair or table it is, it will probably be around 0 for this tool. So we're pretty much, we have the classification on, we have the concept of classification, of labeling what we're giving people, but then we're looking for someone in between. It doesn't really matter. I mean, I don't really want a hard answer. And of course, it works both ways, right? I can make a regression problem, and then if it's above some value, okay, that is definitely a chair. But I don't really like to work in that way because, again, I'm arbitrary in choosing stuff, and that's exactly what I don't want to do. I want the computer to tell me what it is. I want it to have the freedom to do that. So anyway, linear logistic regressions, you might have heard of these before, and those are the most common ones. Everything in the universe uses linear regression. So economics, biology, everywhere, everyone. If you guys, if one of you has a degree in those fields or have worked with these people, you'll be totally familiar with this. And then unsupervised learning, which is pretty much the same thing, but I don't tell you what it is. I just give it a bunch of chairs and tables. It has no idea what a chair and table is, but hopefully it will be able to tell, okay, you just give me two different things. I can tell that these things are similar and these things are similar, okay? I'm not really sure what they are, but I know they're different, okay? So when there's canary clustering, there's k-means clustering, and the k there, it stands for how much, okay, I'm giving you this data. I think there's like 3, 4 guys here, so make your best guess. And this is usually very helpful when you don't really know what you're dealing with, you're exploring. So you get this bunch of data, you don't really know how people behave or how things should work. And then you do that as a part of the exploration phase, and then you understand, oh, this is a table, all right, let me write that down for you, computer. And then you tell the computer, this is actually a table, and then you can move on to a classification problem or a regression problem. And also in that vein, you have decomposition, which is, okay, I have way too much data about tables. I know I have the color, I have the material they're made of, I have their height. So this probably won't fit an algorithm if I want it to run fast enough. So let me try to figure out which one of these guys are the guys who are most significant for telling apart if it's a table or a chair. So probably height will be a good measure. So if the base of it is closer to the ground, it's probably a chair. And if it's a little higher up, it's probably a table. I mean, that will fail for a long... If you only use that, you will fail a lot. But if you were to decompose this, you would find that that's probably one of the highest things that impact if you're going table or chair. Anyway, that's machine learning, okay? And I appreciate there's like people who devote their whole lives in studying this, but I just wanted to make sure that you guys understood what the kind of vocabulary that we have, okay? And if you are, when I first got exposed to this, I was, okay, how can I use this? Okay, this sounds like a lot of potentially good applications around that. And the thing that you have to be careful about machine learning, I mean, not only trying to get some statistical sense of what we're doing, that definitely helps, so you don't reach some weird conclusions, but you have to be very careful with the data that you choose, okay? Especially in security, you might be fed bad data, okay? And I think, I'm not entirely sure yet, but I think a lot of machine learning attempts on information security, they were trying to do too much too fast. So they would get a lot of data that you were not really sure if it was bad or not, and just trying to infer some sort of conclusion from out of that. And I'm starting from a much lower bar, and we'll get to there soon enough. But you have to be very careful. The point I'm trying to make here on this slide, you have to be very careful that you're reading the right mark, okay, as far as the bias is concerned. And the variance, there's really not a lot you can do about that, okay? Sometimes it's just random noise that you can't really control any shape or another. But if you get, I know it sounds kind of weird if you don't have a statistical background, but if you get enough of this data, all of these weird noises will kind of cancel themselves out, you know? And if you add everything, that's how it turns out. But the point here, if you take those two things into consideration, okay, things will get better with more data, all right? So that thing on the right there is from one of the online courses that I took. It was from Caltech. It was really, really awesome. A lot of the mathematical background in there. And they were like, okay, so there is an error. There's an expected error. You're not going to get 100%. And they're not designed to get 100%, especially because of the noise, because of the different problems you may have with data ingestion. But you can get to an expected error. As you get more data, you'll get what you call the error inside your model, which is the data that you trained it with, and then the error outside the model, which is, okay, this is the data I've never seen before, and I'm trying to generalize these calculations that I did here so that it can fit a larger purpose. And of course, we have to be careful with adversaries, all right? So as soon as we start developing these machine learning things and we start working with integrating them into our security tools, people will figure out how they work, okay? And I talk a lot about how it works, and I talk a lot about potential attacks to it, I mean, the few that I've already envisioned. I mean, what we have to be conscious about is the way that spam engines involved as well. So at the beginning, when the Bayesian filters started getting some awesome press, you know, they were doing a pretty good job. So what did people start to do? They would have the original Viagra or meds text, and then they would paste like a whole sonnet of Shakespeare at the bottom, right? So that it would completely fool the algorithm, because it was looking for words that, okay, this is a word that's not likely to be in a spam. So yeah, this is probably very unlikely to be a spam, because, I mean, nobody uses thou in a spam. So yeah, that's how they think, right? They're pretty much counting words. So every time someone tells you they're doing feature engineering, it's just a fancy word for counting, okay? Bear that in mind. They will sex it up as much as they can. But it's basic counting and trying to create inference based on the probabilities of one thing happening and the other thing happening. Anyway, so that's it for like the introduction piece. How am I doing? I am okay, halfway. And now I want to really get into an example, okay? And again, the counting is the most important thing. If you count the wrong things, if you give the wrong features to your model, it will not decide anything, and it will not bring you any different results. So this is one of the things I put together on this research that I'm doing, and I'm going to talk a little bit more about it later. So what did I do? Okay, so I got a bunch of firewall data. Okay. And then you have firewall data, firewall block data, not even firewall data. Come on, man. This is the crappiest thing you can get. That's like the lowest thing on the barrel, right? Why would you even bother? And the reason, where I was coming from is that I wanted to make sure that the data I got was as pure as possible, in the sense that, okay, there's absolutely no way that this guy port scanning the hell out of me was up to something good. I wanted to make sure that I had a very good ground truth on the data that I was ingesting, so that I would be able to, whatever inference I get out of it, okay, no, I'm fairly certain that the data that originated this was from people doing bad stuff, okay? And that's, again, like I said before, that's one of the greatest problems that we have to face. Okay, and the current solutions, they don't really help us that much. Okay, so pretty much the way I designed it is that anything that can get you a very positive confirmation of bad things. So yeah, this was a critical IPS block. You know, this was a firewall block. This is a very bad WAF application firewall alert. Okay, yeah, that should be bad, right? Let's pick these guys, and let's summarize that, okay? So what you get here is just a sample of a day. From SANS, you see it's got like about 1 million rows. So each row, it's pretty much an IP address was seen doing bad things on some port, okay? And so the D-Shield program, actually they get a lot of volunteers from around the world. Although I would think that most of them are from the US, they wouldn't really tell me, and I totally appreciate that because of confidentiality reasons on their program. And if you go to their website, they'll have a lot of, top 10 ports that are being attacked, top 10 IP addresses of things that are coming from. But if you ask, like, nice enough, they will have you have a look at the bulk data, and that's pretty much what you get from the bulk data. That's cleaned up, and that's R, by the way, if anyone here is a stats buff. R is awesome. So anyway, this is an idea of what I got, okay? So I started on January 1st, so that's up until almost today. I think I generated this graph a couple of days ago. So on average, okay, the mean actually that I'm getting is like 100 observations a day. So 100, this IP address did X amount of things bad on that port, so that's an observation for me. But if you actually count the amount of events, so yeah, this guy did bad things X amount of times. It's closer to 30 million events. So I just wanted to point out, this is not big data. Hell no, I'm doing a lot of these calculations on my laptop, okay? And it's not even the best one you can get, you know? So it's, I mean, just roll your own in a way, and we should be seeing much more things than that. We could potentially do much more things than that if we had a lot more data. So what's the intuition here, okay? We need to create the features, okay? And counting the IP addresses is not enough. Counting the IP addresses mean I've just created a new blacklist for you. Thank you very much. So we have to aggregate these guys by some measures, okay? So that I can actually, okay, if this guy did this, it's possible that the fact that he did this has an influence on a different group of IP addresses. And so I got this idea, okay, let's try to find a proximity measure, try to find some sort of similarity measure between those IP addresses. And then I came across this very cool concept that everybody seems to talk about in incident response, which is the bad neighborhood effect, which is pretty much, there are some places in the internet that are more lenient, okay, with potential malicious behavior than others. So if people are trying to do something to you, they're trying to attack you, they will have an easier time getting an IP address consistently on those places than other ones, okay? So, of course, it varies. I always was substantiating this with data to make the decisions, and that's pretty much one of the measures that the algorithm uses. So I have some examples here, which was, I mean, the Spenhouse versus Cyberbunker stuff. I'm pretty sure you guys heard about this story, but there was a time when Spenhouse, I quit. Just block the whole of Cyberbunker because they don't care. They will just spam the hell out of you. Doesn't matter who you are, doesn't matter where you're from. And it's in a way an indication of, okay, these guys, they have the tendency to do that. And okay, and that created like this huge DOS attack, but that's not what this is talking about. The Google report, the Sparrows report on malware got to the same conclusions. They said, okay, there's a lot of malware from this region, okay? And it's not because, oh, there's an evil state actor there that's doing this. No. That's the guys that let you host malware. So there is a trend going on. And the last thing I wanna say, it's a paper. This is a PhD from Brazil actually, that he did like a whole more data mining than I did. It was like 5 years of data mining out of Brazil's research network for universities and things like that. But I said, okay, this is blatant. Okay, I can totally see that there's a statistical significance on these guys coming from specific different addresses. It's not random at all. So if it's not random at all, we can probably use this to our advantage on this model. So, in a nutshell, grouping by net block, okay, which is completely arbitrary, but anyway, you gotta add some arbitrary things as well, and grouping by some ASN measures, and I've been using Team Kimmer's service. They're awesome. So this is just an idea, okay? I'm not sure if you guys have seen this before, but this is an attempt to represent the internet, all right? This is pretty much a map of the internet, and each pixel is actually a whole bunch of IP addresses, all right? And the way you have to look at this is that, first of all, in the higher spectrum, think about 4 different quadrants where it goes like this. So the 0 is up there, okay? The 10 is up there, and you can see why it's hashed out. It's not public, okay? So you move from that quadrant to that quadrant to that quadrant to that quadrant over there, okay? And this is actually called, a construct called the Hilbert curve, which will try to maximize think about the IP addresses as being in a line. Okay, from 00000 to 255. It will try to maximize the proximity of these IP addresses. It's actually a fractal. It's actually quite pretty if you get to draw the fractal. But this is a kind of map that will better show if something is going on by grouping of internet IP addresses. And by the way, the star is where we're at now. So if you're at the BlackHat Wi-Fi, that's where we are, that you are here. So it's not random, you know. There is a lot going on potentially aggregated places. Okay, I pointed out some guys who are very popular. Okay, and I added Brazil there just so people didn't think I was speaking on different places. So you get a little bit from there. I mean, there's a whole lot of other Chinas in the map. They have a whole bunch of IP addresses, a whole lot of other Russians, a few Brazil. Brazil doesn't get that much. But you start to see it kind of wants to cluster, you know. Maybe if we give it more data, it would be a little bit more visible. And what you see, okay, if I took a sampling of the 10K IP addresses that were happening the most frequency-wise. And yeah, there's a lot of China there, a lot of Brazil, you know, and you can see that what would indicate a little bit of this clustering, okay? But, I mean, you just have to be careful, right? We're not out to get China. If we look at, the US beats everyone by far, right? They will consistently be scanning other guys. And I mean, based on my assumption that most of the SANS data is from the US, yeah, we're pretty much scanning each other, right? The threat is everywhere, potentially. So, and I don't really think that country codes are any good measure. So if you're just like, okay, I'm blocking China off my firewall, yeah, that's not going to do a whole good for you, especially because of anonymous proxies, and I'll touch on that a little bit later. So the second intuition is about temporal decay, all right? So even bad neighbors, they renovate, right? So you want to kind of get like a temporal analysis of this. So if something happened like a few months before, I don't really care. If it just happened there, okay, I'll give this guy a chance anyway. I don't really need to care about him. I mean, of course, we're all very paranoid, but not everyone is out to get you at the same time, okay? Just a subset of them at different times. So let's forget bit by bit who is attacking us, okay? And we just do an exponential decay function, all right? So, I mean, I got some ideas there. So this prototype was built based on daily data, all right? That's as frequent as I would train the model. So that's actually number of days there on the horizontal axis. So, I mean, after 100 days, no one really cares, right? I've pretty much forgot what was happening. But then, yeah, that's it. But then we need, so based on this intuition, all right, we calculate the features pretty much how I described, okay? So first of all, you choose a behavior you're trying to predict. So I was showing you people that were blocked on port 22, okay? And the leap here, the inference I'm doing is, if people were consistently blocked on port 22 on the internet, if this guy knocks on your door, he's probably not up to good stuff, okay? And we calculate this different ranks, this different ranking for IP addresses, and that's through time. So each time you calculate a rank for a day, you actually want to get the previous one you had for yesterday, you decay it with the function, and then you add like 1. Measure, okay, I found this guy today, so I'm adding 1 here on this rank. But if you're looking at the NAT blocks, and you're also aggregating features on the NAT blocks and on the ASNs, you're actually, I actually want to be fair. So if you are in a very, very large ASN, I want to make sure that your contribution to that is only according to the size, of the ASN. So if you're on an AS that has like 10 IP addresses, okay, one guy will make a lot of difference if that place is to be found to be malicious or not. Okay, but if you are in, I don't know, /16, /12, yeah, you got to get a lot of people in order for that to actually matter in a way as far as the features are concerned. Okay, we still got missing ASNs, we still got bogans for some reason. Okay, and yeah, you have to handle them separately. And I kind of ducked out of this, so I just, okay, these guys are obviously bad, you know, but there are of course different ways for you to handle this data. It's one of the kind of exceptions that you have to program for. So, like I said before, you know, you kind of have a day rank. So for each day or for each time slot that you have, you want to make sure that you're calculating against it. And yeah, you can cheat. The CyberCat is looking at you. But of course, the training data, if you need a lot of it, you need to go through multiple days. So you want to make sure that while you're creating your training matrix, that this is working through each day that you work with. Okay. The problem here is survivorship bias. All right. If you're trying to predict something that happened, and I'm talking about log data here. It's not necessarily real time. If I want to predict something that happened on March, I don't want to use data from July. That doesn't make a lot of sense. In a way, I'll be peeking into the future, okay, and that might help or hinder what I'm doing. So I'm just going to go really quickly through this. I just wanted to give you guys a taste of what the distribution looks like. So this is so you're accumulating this. So each rank, the following day, it is the previous rank decayed by this exponential feature, and plus 1 if it showed up or not. And you see a tendency it stabilizes on the last few months, on the mean and the median you can see there, because, I mean, pretty much new people are coming in and old people that I've never seen before are coming out. The cool thing is that the one there, the guy who is one, is a guy who's shown up every single day. Okay, that's how you get a one there. Okay, so that's on the, this is actually a log scale, otherwise it would be impossible to see. So we're talking about a 10,000, yeah? No, 1,000. Yeah, 1,000, that's 3 there. And by there we're almost on the 10,000 of people who are in the one. If you were just doing like, okay, I'm gonna do a blacklist. I don't care about this, you're crazy. Let's do just a blacklist of these guys, right? That should be useful. What you would be considering, okay, and this is let's say you take a week out of this blacklist. You're only considering pretty much at the 1.5 mark over there, because if I'm decaying by 7 days, after 7 days, the guy only showed up once, it will be like half. So look at how much data you're leaving out, okay, that could potentially be used for inference. That's like, that's 5 there. It's, oh God, 100,000, right? And a lot of that, okay, there's a lot of stuff, okay? And this is the same thing for part 22. I mean, it's the same idea, just to see that from different examples, it kind of relates to each other. So, good. I warned about the math. So, yay, bunch of numbers, right? That's awesome. But then here's the thing, okay? We have the numbers, which are our features, and we have the label. We know these guys are malicious, okay? So let's create a model to predict this, okay? I don't want to have to choose at which rank something becomes bad, or at which AS rank, and that's the whole point. If I give it enough examples, after I've calculated this and tell them what it's bad, it will tell me. It will create a very complicated function. I have absolutely no idea what it is, but it will make sense consistently with the data that I fed it. So that's about a rule of thumb of the number of observations you should have. And so sometimes you have to get multiple days, and that's why the not peeking ahead is necessary. So a good point is that we need non-malicious IPs, okay? So a very cheap trick there is that you just tell it everything is malicious, okay? So just tell it, okay, it's easy, just one, right? Everything, you're not giving me any other example. Everything is a chair, right? So I also gathered some non-malicious IPs, okay? So quotes from Alexa and Chromium top 1 sites. So I mean, probably Facebook's not out to scan you. So I used that as a reference on how we should build this. And yeah, I'm running out of time here. So put on the features. I got my training table. I chose support vector machines to use that. So this is just a quick summary of what it is. And I guess what's important here is that it is good for classification problems with numeric features, okay? Has a lot of built-in functions there. It's something that came up in the 90s. It's actually for a machine learning algorithm that's actually quite late. So it's quite good, and it can create an arbitrary complex function out of the data that you give out of that. And you don't really have to know. So it's going to calculate something on an infinite dimension in order to give you back the feedback that you wanted, to classify if something is good or if something is bad. So what does it look like? Okay. So doing that for a few ports, all right? So I selected some ports. I would get a training accuracy. And accuracy means that, okay, this is what it got right based on all the stuff that I gave it, from 83 to 95%. So 95% was for RDP. It was pretty good. I had a lot of data about RDP. For some reason, people love to scan that. But for port 22, yeah, not so much, more like the 83 stuff. But that's training accuracy, right? I use the model itself to tell me how much it got right. That's not really, really good, especially since I'm using time-sensitive data. It really messes up. It can mess up some things. So on the new data, so training a model on the day D, and then going for the D plus 1, we got like 75 to 95%. So in roughly increasing over time, and that's the point I'd like to make here, is that if you look at, so that's different dates there, February, March on the right-hand side. And then as time, of course, it got a hiccup. Sometimes it does on March. But you can see that, okay, this looks like, as I got more data into the model, it was getting a little bit better, okay? And this is an idea here of how the models, they fare against future predictions. So again, if I'm going to predict something for the D+1, I really want to use the D model because that will obviously work much better. So you see, I lose a lot of stuff. If I try to use the model from February to predict what happened in July, a lot of things have happened, and I don't really have a good grasp on what's going, which also exacerbates the thing I was doing about timing and about the landscape changing as it goes by. So yeah, this is another example. It really lost itself there on April for some reason, but this is for 3385. So what's the point, okay? And I want to make sure I get this point across. With new data, we can verify that we got like a 70 to 92 true positive rate, and that's called sensitivity or precision in some circles, especially the medical circle. And from 95 to 99 true negative, okay? What does that mean? That means that if this model tells you that something is bad, okay, it is from 13 to 18 times more likely to be bad than something that it didn't tell. Okay, so if you're in an analyst chair and you're trying to make sense of what's going on, if you had something like that that would push to the top of your screen these guys, okay, that you actually accumulated this knowledge over time, that would be a great help. That would be a great help for what's going on. And this is an example of this output. Okay, this is actually not an actual output of what people get, but this is the same Hilbert curve. And you can see that for some places, and this is like doing 100K randomized IP addresses for each class A, it will definitely think, okay, some places are hotspots. It is about 100 to 1,000 times more likely that someone is attacking me from that neighborhood than the other places, okay? That in itself doesn't mean a lot because, okay, how likely it is for someone from this place attacking me. But here's the thing, nobody really knows the priors. So if you're using some measure to bring something to your attention, okay, this seems to be more important. No matter how unlikely it is for people to be attacking you, that definitely has some value. And yeah, those are the guys we saw before. Okay, how does it break? IP addresses are terrible, right? Forget about UDP, all right? And any person who does DFR knows that doesn't work. Again, this is not attribution, this is defense. I don't really care who these people are at the moment, okay? I'm just trying to make sure I see this stuff. So, challenges, anonymous proxies. Not really, because they share the same properties. So people who are lenient to have anonymous proxies will be lenient to have hosting malware and things like that, so you can kind of translate that. Tor, not so good, because it doesn't cluster as well. It's much more random and distributed. I haven't really done a lot of research on that specific area. And if you're like, okay, I'm a lead hacker, I'm going to change my IP address every 3 minutes when I'm trying to, yeah, okay, forget about it. You got me. But the point I'm trying to make here is that this is looking at IP addresses. And if we can build similar features for different actor types, okay, we're probably going to get somewhere. So, as it is, it could really help SOCs, I believe, to help with triage. It will not do your DFR. It will not do instant response. I mean, poor computer. But the boring task of eyeballing everything, okay, and making a decision out of this eyeball, yeah, that definitely can help. So when you start getting different algorithms together, okay, so I did this prediction on the firewall, this prediction on the IDS, this prediction on the WAF, and you compose this model, what's called ensemble. So here's this guy's telling me it's bad, this guy's telling me it's not bad, this guy's telling me it's bad. You could get a very high confidence level. And you could get to the place where you're blocking this. Or, I mean, even better, you're SDNing it. So if this guy is like 50% more likely to attack you, I want this guy to make a bigger path on my network. I want him to go to additional scanners, additional IPSs. Yeah, I'm not blocking him. I just want to make sure that, this guy, I'm checking up this guy for everything that is up to do. Anyway, just want to finish up. This is what I put together. So I'm basically begging for log data. Okay, I got a lot. And the idea here is that this is all fine and dandy, but it really works very well for the logs from SANS, right? So as we get different places from the internet and we get different ideas, this general model can evolve. And of course, a similar model can be built specifically for your organization, leveraging the same kind of knowledge building to reach potentially similar levels. And you get a nice report. It's not very fancy, which tells you what's good and what's bad. So anyway, you can just hit me up there. I just want to reemphasize this. This is really the beginning, okay? And I'm really glad to meet anyone who's been doing work like this or has similar ideas or think I'm completely nuts, because I just think we need to get the conversation started, okay? I think this is going to be an issue. This is definitely going to be an issue, and we might just lose a whole bunch of security monitoring, good security monitoring people because of the intractability of the introduction of big data into it. We're going to need these robots to really, really help us. And that's it. Thank you very much.